Hey, good afternoon to everyone. Just curiosity I have, how many people work here in image processing and video processing? Can I just have a quick count on that? Not many? Okay. Well, this talk I'm going to deliver about is for the application area of image processing and video processing, I had come across some problems and how I got through for a solution. That's what I'm going to share with you today. In a quick look, we are going to have abstract what I really mean with this title of image to VHDL translation, and I'll also introduce with the potential problem areas or potential opportunity areas that we are highlighting this as a solution. And we'll also go through a quick how the implementation takes place, how implementation can help us. And a block approach will be giving us a pictorial details going about the solution. Then there is a necessity that we have images of different file formats, and how do we really take them into account in our system, in our solution, that we'll talk also about. And essentially when we are talking about VHDL and Verilog or any HDL, we come across factors like synthesis and simulation. So how to integrate about this solution into our simulation and synthesis, we're also going to be talking about that as well. That will be more helpful for those who are going to include this solution for their simulation as well as for synthesis. And let's summarize finally what benefit we have got. To keep the focus, this is dealing with essentially applications that are using VHDL and Verilog. VHDL is the area where I'll be limiting my discussion today. And the area of application is going to be again video and image processing, as I mentioned earlier. Now, having integrated and hard integrated systems or VLSI systems, we can expect some kind of a hard real-time response, and that is what the quick aim or real objective of this solution in general. So when we are dealing with images and videos, so any image is a representation of a two-dimension matrix. So when we are going to test a design or exercise any design for image processing, maybe it filter or maybe it compression, we not only want our design to subject under any two-dimension matrix, but instead it will be worth subjecting the design or for testing with the real images. And that's where the area where our solution is going to work for us. To introduce a little about a problem, well, let's try to understand the image representation and the key parameters that we are going to take into account for this kind of solution approach. And essentially, we'll be handling 8-bit image resolution. Why 8-bit? I'll justify quickly in forthcoming slides. Apart from that, typical video application was something motivation for this kind of a solution that I came across. Going ahead, what goals we really need to be focusing on for this kind of solution is, well, we have to have some methodology where any image, any picture is translated into a two-dimensional matrix as a ROM, as a read-only memory. That's how we are going to reuse in our VHDL and Verilog simulation and synthesis as well. When we are dealing with pictures, well, first and foremost, the format, what comes to our mind is the BMP format, which is very common over different operating systems in industry. So we can deal with the BMP images as a basic reference. Going ahead, our key interest will be essentially to make a reusable component and simulation synthesis models for a ROM. One of the target can also be to have a output in standard HDL where we don't target to a specific technology. I mean, there are many tools existing in vendor market. So they mainly target their own technologies, their own devices like FPGAs specifically, or some ASIC and their libraries. However, we'll make it more standard, more generic, so that it can be adapted in several technologies. Going ahead, when we are dealing with images, we have to identify some key parameters. One of them is the image size, and accordingly we'll generate the ROM. The ROM that we are getting will have to have some known size in 2 dimensions. So when we are dealing with the format of the image, essentially this is a quick representation of how a bitmap image is being divided. There are 3 fields: header, information, and actual data. The header is comprised of a magic identifier which identifies the BMP file format, and that also holds the overall size of the file. Now this file size is perhaps not very useful for us, but following to this there is an offset. Offset tells us where actual image data is residing in BMP file. Apart from that, from the info field, the key parameters of our interest are lying, which are height, width, and resolution. So there can be several ways, different resolutions available: 16 bits, 24 bit, 8 bit. 8 and 24 are very commonly used these days. And essentially then what we deal with actually is image data. So let's say if our image is roughly around 512 into 512 again, or 1024 or 1024 kind of resolution, then 1 megabyte or 1 mega into the number of bits that are being used for representing each pixel will be the size of data. So out of this, how the division in 2 dimension is going to be, that information will come to know only from the info field, where we have information about width and height. So finally, what are the key parameters of our interest? Yes, offset, where our actual image data is lying, and width and height of the image, bit resolution per pixel, and image data. Going ahead, I was talking about 8-bit resolution. So the 8-bit resolution is very limited. However, a true direct color system is being used for image representation. So our eyes, our human eyes, are capable of responding and identifying these colors which are being distributed over 256 levels using 8-bit. So 8-bit should be fairly enough. So when we deal with the red, green, and blue as basic component of a color for any pixel representation, the red or R can be expressed in 8 levels, green is expressed in 8 levels again, and blue is expressed in 4 levels. So essentially that gives a distribution of about 256 levels for a whole pixel of entire color comprising of RGB, where R and G are in 8 levels and B is in 4 levels. This distribution is uneven, and despite of that, the only reason is the normal human eyes are less sensitive to the blue color. And this is one reason. The other reason is that what came across in my reading is that our electronic equipments, from power perspective, blue color has a tendency to consume less power. A typical video parameters these are. I mean, again, when we are dealing with video parameters, we have horizontal parameters and vertical parameters. These are some of the timings. Our area of interest is the frequency that is being taken for horizontal scan, which is a 25.175 megahertz, and horizontal pixel typical distribution. Even the present distribution, what we are seeing here on the screen, is 640 on the horizontal line, and vertical we have 480. So this gives approximate our ratio of what we call 3:4. This is a typical distribution of horizontal sync and vertical sync, how they are being signaled apart, 6.60 microseconds and 1.43 milliseconds for vertical. So it's like 640 comprised for one horizontal line. Like this, we have 480 horizontal lines comprising one vertical. Now from implementation perspective, let's try to understand first of all the image. If the image is typically a 24-bit, and that we need to convert it into a 8-bit color. Now why we want to do that? Because our ROM is byte wide. So any ROM data being accessed will be 8-bit wide. So with that in mind, we need to translate this 24-bit, or we need to compress each pixel level also into 24-bit into 8-bit. Now how we do that, we'll see that in a successive slide. A quick representation of how a VHDL ROM can be represented, we'll also take a look at that. And our key interest is having two-dimensional ROM. So what kind of a two-dimensional ROM representation comes in, we'll go ahead in particular steps. So this is how red, green and blue from their 24-bit representation is being compressed. So we take the plus sign here, what we see, we can consider that as a logical OR. So red, 7th and 6th are ORed in order to get a single color pixel for C7. So 3 bits of the color pixel that we are getting at output, that will represent only red component. Similarly for green, and for blue we are ORing 3 pixels out of available 8 of the blue. So this way what we have essentially is B0 and B1, G0 and G1 and R0 and R1. These are redundant bits which we can ignore. So their intensity essentially is going to be very less. So even if we ignore, that is not going to make much difference in the final pixel that we are getting. So this is one level where we are having a good compression. And unused bits are here redundant, and that's how in 8 bits we accommodate 256 levels. So when we are talking about ROM VHDL model, there are 2 ways, 2 very commonly adopted ways. One is can be just created by declaring constant. So we declare one constant and access that constant array with the address, and the second is just as a simple function of a case or select lines. But my favorite way of doing is by using case statement and select lines, which is the second. Why it is like that, I'll justify in a few slides ahead. This is a piece of code for representing a ROM by first method. We have seen the first method where we are declaring a constant array, and that we are accessing in our main architecture. This is how a particularly VHDL code for ROM will look like. The one which I was talking about, I'm going to demonstrate the output of that. The only reason here is that if I have to decode anything in the runtime in my simulation for particular address, what kind of data is being accessed at the output, I have to refer to this line where D is assigned to ROM and that particular address, and then again refer to the array. So this is what this way is something which I'm not very fond of. So in the second case, since we have a simple case select of index values, we will simply use that value, and we will come to know that if this is address, and what will be the data. So I'll show that in an actual code. Now, having a quick look at 1D ROM, or the only ROM in one direction, how we can have in the second direction is something we need to understand here is the number of pixels, number of bits per pixel is represented with, if it is represented with n, and we have 2 dimension width and height, then 1 dimension ROM can be made by width and the number of bits in that pixel. So like this, if we have h number of ROMs, will give us a 2 dimension. Now our area of our interest is essentially here is to be able to address in a 2 direction h and w. So every time we'll need a 2-level decoder. So first decoder is essentially going to decode the vertical, out of which all w number or h number of ROMs are being accessed, and out of them only one will be selected for a particular pixel when we want in 2 dimension. So when we are implementing a 2-dimension ROM, the output of each ROM will be commonly decoded by address select line, and from that the output of that multiplexer or that selection is going to be the final output of each pixel. This is what simply means by this slide. This is a graphical representation. We have 1D ROM. ROM 0 represents the first read-only memory model. The h is the final h minus 1, because for h from 0 count we will have 0 to h minus 1. That will be h number of ROMs, and the vertical address selection, we have 2D selection, where output of this multiplexer is the final pixel output. So going ahead, what kind of blocks we really have is the first and the final block we see. Now, first block, which deals with the image to 2D matrix, this essentially just converts the ROM. It decodes, converts the image into ROM, the data that should go into ROM. So it just takes a pixel out of image and generate some database. The database can be even a plain text. And then what we have is the actual HDL modeling. So that two-dimensional image processing that we want, between the input image and the VHDL output, we can introduce that as well. And also debugging becomes very easy. So when I was dealing with these intermediate processes, what we have is a spatial resolution that we can be adjusted, pixel requantization, and pixel requantization is again, I mean, just like now what we saw, from bringing about 24 bits into 8-bit representation. So that's a pixel quantization activity, what we already did. Any other further quantization or resizing can be also done. The geometric transformation deals with that essentially, and resizing and sampling aliasing, that depends on what kind of sampling frequency we really want to use for our horizontal direction or in vertical direction. And histogram equalization to make your contrast balancing. And when we are dealing with different images, I mean, so far the basic image format we dealt was BMP, bitmap image. But when we want to deal with also other format, where we have JPEG, TIFF, some commonly used, and GIF or RAW, etc. For that, we'll have to take into account few parameters, or what differences it has with the basic image representation. So first is the way the data is stored, image data is stored. In uncompressed BMP format, it's a plain data, whereas in case of JPEG, typically this will be a compression after cosine transform. Then how the image is being compressed, so that's where the data of that image deals, and type of information we really are going to get. This really means is that if we look at the GIF format, sometimes we also get the background transparent, or some field of the image getting transparent. So this transparency is one of the information which we segregate, which we possibly need to take into account. When we deal with the image as a ROM, perhaps that feature of transparency is not more available, or we might have to deal with a special technique in our design. So when we have these three things into account, we perhaps not be able to deal with this compression and translation into ROM by plain language. My first implementation was into C, using C programming. So it was difficult to handle these many image formats as well. That's what it really means, that to obtain the key parameters and the image data is not really that easy. Perhaps we might have to go for uncompression, and then we really implement the translation into ROM. But there is one possibility here, is that if we go for higher level languages such as Java, now Java has a image IO class. If we use that, then handling with this different image format becomes easy. There can be other languages supporting distinct images as well, like C# perhaps, and Perl, if anyone wants to try that. But each image, out of each image, our interest is in the content or the actual pixels of this image, which is RGB pixels or data that we are talking about, and width and height parameters, because that's how our two-dimension for the ROM are going to decide, or that will be the input for deciding our dimension of our ROM. Going ahead, when we have our ROM modeled, the model of ROM available in VHDL into 2 dimensions, how we want to use them into simulation. typically in simulation, if we look at it as a blue background as the entire test bench, and we have one DUT model, which is a DUT is essentially is a design under test. We have implemented some kind of compression or some kind of image processing algorithm, even filtering, and for that we need to feed actual image. So we could simply instantiate a VHDL model of the ROM that we created from our approach, and that we can subject for the simulation. This approach becomes very flexible. I mean, in simulation we don't have much constraints to deal with. However, the generated ROM is still synthesizable, runs very well in simulation. Going ahead, when we want to synthesize and implement that in a system, we have to take into account few parameters, just few key constraints. Just before talking about those constraints, this is a typical representation of use of this VHDL ROM in a system. We have one model which is instantiated in a system, and there are other several processing blocks. Perhaps the green may be representing something like a processor. This all in one chip can go as a SoC, single system on chip. But the only constraint here we have to look into is what kind of resources are available. Typically, excuse me. Typically, if we are targeting FPGAs, then we might have to look into the availability of block RAMs on distributed RAMs that are available in order to use them for our ROM model. And of course, when we are dealing with this kind of system, then addressing is also a key parameter, where we have to have a decoding of those many addresses depending on the size of our image. So that will again affect the speed of overall operation. Rather, we'll have to have a system faster to deal with this kind of ROM. So quickly, in short, this is a tool-let, not an entire tool, but a part of a tool, or simply a utility with an intelligence to obtain key parameters from image. We are subjecting one image, getting out few key parameters, and also getting the data out of it, and we are just translating that into VHDL. So what output we get is a pure VHDL synthesizable, which can be used in system synthesis as well as simulation. And one key goal we have achieved here is that we have a generic model of a VHDL where target independent output we are using. And one thing we have to take into account, that when we are using different image formats, then it will be useful to take help of other higher level languages, such as I just mentioned, Java. Yeah, I think I mentioned the first one, which is standard VHDL output, and the way we are integrating in our system and also in simulation gives us seamless approach. And for VLSI FPGA applications, that is what the key motivation where we started our discussion.